All right, so welcome everybody. Today I'm going to talk about a new feature in AllegroGraph 5.0, which we call nDimensional or multidimensional indexing. And so here's the things I'm going to talk about. The first thing is, why do we even need nDimensional indexing in a semantic graph database? And I'll go in depth, but let me just say, users put events in AllegroGraph, and if you want to do event handling on a really big scale, you need something like nDimensional. Then, after I've talked about that, I'll talk a little bit about how it works, and I promise not to go too deep. I'll try to keep it within, well, 2 or 3 minutes, but you need a little bit of an overview of the technology. And then I'll talk about what our customers do with this, or what you could do with this. I'll talk about a little example from legal interception. I'll show you how we deal with some weather data. I'll give a quick demo about fraud detection and the complex queries we can do in the financial domain, and then I'll talk just a few words about moving objects and what we're planning to do with that for the coming year. And then at the end, if you're interested, I'll tell you how you can start with this, how you can go to our website, download some data sets, download AllegroGraph, and get going for yourself using this new nDimensional feature. So first, why do we need nDimensional? Well, somehow, we at France have been talking since about 2007 about events in a semantic graph database. We talked about how you could look at the world from an events perspective, look at people, places, organizations, interactions between them, and how you can do analytics on that. Yeah, and so since that time, a lot of our customers actually use events and store them in AllegroGraph, financial data, telephone records, email databases, etc., and these customers most of the time want real-time answers to geotemporal queries. Yeah, they want to know where something happened, what time interval. But what you see is that the data sizes grow really, really rapidly, and although our customers love our 2D GeoSpatial, they really urge us to go to higher dimensions. Yeah, so that's what we did. Now, to take a step back, when we talk about events, what do we actually talk about? Well, in our case, an event is an object or a set of tuples with the same subject, if you want, that have a type, and we work with phone calls, SMS, email, meetings, credit card transactions, insurance claim, point of sale transactions, hospital visits, etc., etc. In many cases, these types are in a hierarchy, so you need at least some subsumption reasoning. Events always have a start time and sometimes also an end time, and for that you need very efficient temporal reasoning, and so we created a library to deal with that. Events most of the time have a location, and so for that we need our geospatial capabilities. And finally, events always have an actor. Yeah. The sender receiver used mostly, but the phone calls or credit card or whatever you can think of. There's always multiple actors involved. And so for that, if you want to find relationships between events through actors, you need libraries for graph analytics and social network analytics. So some of you might have seen this in the past. So we already for many years sport technologies for geospatial indexing and reasoning, and what we especially specialize in is to make it very fast to find where something happened, how far an event one was from another event, or find all the events that occurred within the bounding muscle radius of so many miles, etc. So that was a library that we've been working in for years. And then because you deal with time, we created libraries for temporal reasoning, and actually we created a variant on Allen's interval logic. And so we have a set of calls for each way two intervals can interact, as you can imagine. So that's been in AllegroGraph for several years. Then we have libraries for social network analytics and graph analytics. So we can tell you how far one person is to another person through a set of relationships that you can define. We can tell you what groups a particular person is in, or how important a person is in a group, or whether we look at a group, whether it's just like, unrelated people, or whether there's actually even one or two leaders in the group. So we have library calls for all of them, and then already in 2008 we could put all that all those capabilities in one query framework. Yeah? And at the time it was only Prolog that we could do, but here's the typical query that I've been talking before. It's find all the meetings that happened in November within 5 miles of Berkeley that was attended by the most important person in Janss's friends and friends of friends. Yeah? So we say find this X, and then we would compute an ego group around the person Jans 2 levels deep using the nodes relationship, and then we would compute the importance of each person, and then for each person we would look if he was in a particular meeting, in a particular time interval, and in a particular geobox. Okay? And so actually most of our customers at the time were in the government, but our, well, more commercial customers also wanted to have this capability in SPARQL. So since 2012 we also can do this in SPARQL using magic predicates. So if you look at this query here, you see the query, did the most important friends of Sonia make a payment within 100 miles of Rotterdam, New York in the last 10 years? And you would see that we could find a place, Rotterdam, in the state New York at a particular location, and then we would find the person. And then here you see, so here we see that the person who has this email address, and then you would see here SNA Eagle Group. Well, this is actually not a predicate in a tuple store, but well, it's what we call a computer predicate. So basically what this line does, it says compute a group, yeah, around the person who, 2 levels deep, using the paid relationship. Yeah. So now we have a group. And then in the next line we would say compute the importance for each person in the group. So for each member of the group here, we'll find the centrality measure. And then we would look at events for these people, and then we would do a geospatial call where we said, well, if the other place where the event happens actually within 100 miles of the location that we found here earlier, etc., etc. Yeah, so to some extent this is a beautiful way to take all these separate libraries and embed them in SPARQL. But as we said before, you see this huge growth in data sizes. Literally, people are working now with billions and billions of events on huge machines, and real soon also distributed. And you want to keep the joins for latitude, longitude, time, or even latitude, longitude, time and amount scalable. Yeah. So we couldn't do that anymore with our patented 2D indexing, and so we went to multiple dimensions. Now, how does that work? Well, in AllegroGraph we have kind of 2 kinds of indices. If you look at the main index, where you store subject, predicate, object, graph, you now have an index-free hash-based adjacency list. But all the other indices, the secondary indices, are append-only sorted quintuples. And most of the time, if you create multidimensional indices, you use some kind of variant of R trees, but storing those in a sorted file doesn't work really well. So one of our colleagues, Steve Huffley, came up with a new idea, and that's to divide the world up in horizontal strips and then sort data within the strips. So imagine this, you have a particular area, we have the longitude here and the latitude here. And then what we would do is we would define the world in strips and then sort the data within the strips. Yeah? So you see that the data type that contains this latitude-longitude pair would have a latitude strip, then the full longitude, and then the remainder of the latitude. And so, for example, say you have defined your world in strips of 10 miles height, yeah, for latitude, and say you have the city Berkeley in there, then if you want to know, say, all the people that live within 15 miles of the heart of Berkeley, then what you do is you first look at Berkeley, you find the latitude, longitude of Berkeley, and then you probably only have to look in this strip or in the strip above and below to find all the places that are within so many miles of Berkeley. Yeah? So instead of doing a join over all the latitudes and longitudes, yeah, we just have to look in a tiny strip, and probably only have to do 1 disk search or maybe 3 disk seeks. Of course, if you make the strip size too small, then you would have to look in multiple strips, but we found that in reality the performance degrades not that much. Yeah? So you have to choose your strips wisely. It's a fairly tolerant indexing mechanism. And what we also see is that our customers sometimes, for the same area, would create an index for, say, a strip size of 5 or a strip size of 100 miles, yeah, depending on the kind of queries that you do. Now, as I said before, this wasn't enough, so we needed to expand to multiple dimensions. And already in 2008 or 9, Steve and I wrote a paper about this, how you can do efficient 3D and 4D geospatial indexing in RDF stores, yeah, and we were especially focused on moving objects. And we now have it as a full production-ready capability in AllegroGraph. It still is the same technique we use for 2D, but now we generalized it to multiple dimensions. So what you see here, it's if you say this is one data element that contains, say, a longitude, latitude, time triad, yeah. You use again strips, so you might say, okay, well, I'm dividing the time in strips, so you have to make a choice there, and then do the latitude in strips, and then you get the rest of the data again in this 80 bits. So now if you want to find all the things that happened, say, within a particular distance from an XYT point, well, sorry, you get the point, yeah? So with this technique, we still have to look at only a very small part of the data set for certain types of queries. And in the paper, we actually describe more and more complex queries, and we talk about the complexity of these queries. So this is very simple, and what is within a given bound from a given latitude, longitude, time. It's more complicated if you want to say find two moving objects within a given distance, or even more complicated, discover all moving objects within a given distance, etc., etc. So the paper keeps going, and describes the complexity of these queries. All right. So now that was the technology. So what do people use this for? Well, one, which was, by the way, the main reason why we had to, why we put this feature in AllegroGraph now, is for legal interception. So you have persons of interest. You have GIS data for important landmarks in the world. So you know where the school is, a factory, office, and where they are. And then you have an enormous number of telephone short messages and location records. Yeah? And then you have rules, yeah, that get fired every second or every minute. And the typical rule would be, one, if 3 people from the same criminal gang are together within 300 meters in a short time window, and then turn off their phones. Yeah? And so this would be a kind of a use case. Now, I can't demo this particular one for obvious reasons, but what we have done is we have created a small test set that we put in our tutorial section on our website. Yeah, with phone calls made in San Francisco in a particular time interval, and we created a simple demo that I can show you now, where we show how fast we can search into in a 3D. Well, sorry, let me take a step back. Sorry. So it's phone calls, and phone calls have a particular time, and they have a location. Yeah. So that's the data that you can download, and then we created a Google application on top that I'm going to show you now. Oh, here it is. Yeah, I hope you can read it. Maybe I can make it a little bit bigger. So here you see a map of San Francisco. Yeah. And here you see the latitude and the longitude that we've chosen, yeah, by clicking on the map here. The radius in kilometers, the year, the month, the day, the hour, the minute, the seconds, and the number of seconds that we want to look around this particular point. So I can click on a point on Google Maps. Okay. Yeah. I'm looking at another screen right now to see if it really actually even works. Okay, right. And I could say, well, I want to look at 0.4 kilometers around that same point. Yeah. So now you see it's got many more phone calls. Yeah, the update over WebEx is really slow. I can also say look at 800 seconds around this point, around the point that we have here, and I can say yes. Okay, let me get back to 400 seconds. And I can just click on any point in the map. Yeah. Now in my screen it's totally instantaneous. I'm sorry about it. WebEx, it's not really good for, yeah, I guess for most people it should show fine. Yeah. Anyway, this is a really fun data set to play with. And the geospatial part is usually done in milliseconds. And I would say try the data set and play with it. All right, so going back to my presentation. Another demo that we did is the climate data. If you go to this website, madis.noaa.gov, they got many really cool data sets. We took some weather stations from the state of California, yeah, for the month of December, yeah. And we're also going to put this data set, by the way, on our website so people can play with this data set. And in this data set we have, well, weather stations with a longitude, with a latitude, longitude, and an elevation. And then we have the real data, which always has the weather station, a comma separated file with the weather station ID, the time, humidity parameters, wind speed, wind direction, etc., etc. And the kind of queries that we do is, for example, find those areas in California that have very high humidity and wind over 4 meters per second in the last month. Yeah? And I have a little demo for that too. So I can, and again, I have no idea whether this will work very well on WebEx. Give it a second. Yeah, I'm waiting to see it on another laptop here. Okay, so let's start with high winds and high relative humidity. Yeah? So at the top here I have a slider where I can do an animation. So what you see here is the month of December, and what you see at the top of the screen here is December 1st at 8 p.m. Yeah? And now we start running. Yeah. And what you see is that we actually have 2 big storms, but these storms happen mostly totally in the northern part of California, more in the northern part and in the Sierra Nevadas. And if we then go in the next month, sorry, the same month again, but now we do high wind and low relative humidity. And I go back to this place. Then you see that actually most of that activity is almost on a daily basis and much more in Southern California. So I play that again, and I hope you guys can see it on GoToMeeting. You see it in San Diego, Los Angeles, a little bit in Nevada, and in the Sierra Nevada, and then again in the south of California. Yeah, but a totally different pattern. So, oh yeah, the other thing that you see is that there's almost like a daily, every day they have the same high winds and the low humidity. So this is an interesting way. Now, I want to make one caveat here. This is a simple, well not, this is Google Earth. There's much better programs to show this kind of data, say, products like MapSense, but we thought it would be fun to show what you can do with Google Earth and AllegroGraph at the same time. All right, so that was another use case. Yeah, so what I showed you was, well, these 2 kinds of queries. Yeah, that's enough. Then for fraud detection, so we have data from an online bank, yeah, of where people can make online payments. Accounts that are opened at a particular email address with a particular IP number, so you can kind of find out where the place was where the account was opened, linked to bank accounts. And then you have transactions. Yeah, you have the sender, receiver, time, and IP address again, the place where a particular transaction was made, and the amount. And there are some talks on our website where I talk about fraud detection in much more detail. I just want to keep it very short for now. And so here is I'll show you a graph, and I'll show you how the data looks like. So I can find a particular person, say Bruce. my database. And I can double click on this person, and you'll see that Bruce opened his account at a particular time at a particular IP address with an account number and a place, which is Fredericksburg. So if I click on Fredericksburg, I actually jump straight into GeoNames where I have the longitude and the latitude of Fredericksburg. Yeah. But at this place, you can actually also see here all the transactions that happened in this place. But let me go back. Now actually, let me go to the graph view. And I can click on this person and I see, well, all the payments that he made, and I'll just choose a few to keep it simple. So here's transactions, and let me look at one transaction. So this is a transaction between Bruce Hurt, the blue one here. This is the receiver. This payment was made in Fredericksburg too, etc. Yeah, so this is the data that we have, and then I can actually play with this and follow the graph. Yeah, and I could say, is there a more direct link between Darla and Bruce? Oh, there probably is. Now, okay, this is just to give you an idea of the graph and the data, and then the queries I can show you in AG Web View, where this is the web interface to AllegroGraph. I could look at the saved queries. I have one that I actually talked to you about before, and let me make it a little bit bigger. Yeah. So you might remember that the most important friend of Maricela make a payment within 100 miles of Mineola in the last 10 years. Yeah. And I can execute this query, and here you see the results. Yeah, the amount, centrality. But this query still does GeoSpatial and temporal separately. But what we can do now with AllegroGraph is we can do the query in this way, now with nDimensional, and now we can do it even more complicated and faster. We can say, well, did the most important friends of Maricela make a payment of more than $1,000 within the 100 miles of Mineola in the last 10 years? And now here, what you see is that all the filter expressions for time and filter expressions for amount are now put into one call, the bounding box call, and here we say, the predicate I'm looking at is place, time, amount. So this is the nDimensional index that we created, yeah, where we know the location, the distance within the 100 miles, the minimum time, the maximum time, and the minimum amount that we're interested in. Yeah, and this now is not a join between at least 4 or 5 parameters, but it's just a direct, probably one disk seek to get straight to this point. Yeah, and give you the results. So now you can use this real-time in fraud detection. And then finally, and I'm getting to the end of my talk almost, is we've talked before about moving objects. We're talking to several companies that are interested in using this technology to track, for example, trucks, swarms of airplanes. People are using to track soldiers. We've been talking to people that want to look at for endangered animals. And there's many, many applications in telecom for moving objects. So expect more talks from us later this year about moving objects. And then finally, how to start? Well, actually very simple. Go to our documentation. Yeah, we have a full introduction to nDimensional, how it works, and how to get going. So we explain how the encoding in 2 dimensions works, how it works in higher dimensions. If you have to create these IDF data types, it's almost impossible to do that by hand, so we created a wizard to help you with that. And then we'll show you how to do this in SPARQL. And finally, this is the call location example that I talked about. Yeah, so download 5.0 from our website. Yeah, we have a free download up to a certain number of triples. You can download the nDimensional data for telephone records, and then load data and try the queries from a tutorial. And if I get more than 5 requests from the audience today to make a Google program available, then we might make that program also available. Yeah? And then finally, one thing I want to show is the GeoSpatial Data Type Designer. So let me see, where do I have that? Steve, I probably can go to your late 8. No, sorry, I have to go to 20, is it 26? I think it's 26. 28. Okay, there it is. Yeah, so I'm, oh, sorry, I'm waiting to get there. Okay. So you now probably see my AllegroGraph view for 5.0. Now what happens if you want to make these complicated SSD types? Well, here is how you can do this. You go to the utilities, GeoSpatial Data Type Designer, and we've given you two examples. So here you see the data type that you have to copy into your Java program or whatever when you start creating your own data. Here's the subtypes that you can try. Yeah, so let me just try, for example, latitude, longitude, and time. Yeah, I can try it, and you see you get here a box for latitude, longitude. You see the minimum, the maximum, the resolution that you want, and the strip width that you want to achieve. And then here you see the time. So now say I want to add temperature to this. Yeah, I can just say temperature. Temp, and because I can fill this in, it's all kinds of errors, but they'll go away. And I say, well, it's a general data type. The minimum is 0, and the maximum is 100. Yeah, and then maybe a resolution of 1 and a strip. Oh, for time I also have to strip. Let's say take 1 second. Yeah. And so now what you see here is we have the full data type, yeah, that you can stick into an RDF object. Yeah. So don't try to build these things by hand. Yeah, just use this designer. It makes it a lot easier to not have any mistakes in this. All right, let me go back to my presentation. So our conclusion is that what we found is that nDimensional indexing can get you sub-second response times for complex multidimensional queries in event databases. It's very straightforward to work with. Most of the complexity is hidden in the data type designer and the SPARQL magic predicates to make it easy for you. And if you have any ideas for new applications, just let us know. Yeah, we're just an interesting technology to work with, and we'd like to know what customers and users want to do with this. And that was it. Thank you very much. Any questions, Greg? Yep, there we go. Someone asked, how is this different from composite indices? Well, I mean, composite index in relational databases, basically you just stick these multiple columns next to each other, yeah, to make joins easier. But what we've added to the composite indices is also that we use strips. Yeah, so we can do a pre-selection to look at even a smaller selection of your index. Yeah? And as I said before, our goal is always to find the right strip size so you can get with one disk seek or one memory access to the place where you know your data will be. GeoSpatial, someone says doesn't work with GeoSpatial. GeoSpatial isn't yet to the point where they can do multiple dimensions. Yeah, so I mean, at some point they probably will get there, but GeoSpatial doesn't work for the many dimensions that we have. Okay. Another question. Oh, can you do the legal interception query again? Well, yeah. The question that one of the queries that really complicated is where you say, well, did the boss of a criminal gang call at least 3 of his gang members within an hour, and then in the next half hour they all moved to the same spot within 300 meters, and then in the next half hour they all turned off the phone, yeah, and then warned me. So that is the query again. Is this supported in the prolog Lisp interface? Yes. Everything in the AllegroGraph is always supported in the prolog interface. It's always a little bit more work to fit it into the SPARQL paradigm. But yes, everything is supported. Where's the phone call data? Actually I showed it in the distribution. It's in the distribution. Oh yeah, actually that's a good point. It's in the distribution. So I showed it here. So if you download AllegroGraph, then in the directory tutorial, you will find this thing called phone call for TTL.gc. Yeah? And we'll also make at some point the weather data available. Yeah? Okay, more questions? What is the nDimensional capability support reachability to get a path? Okay, then to find path and not external using SPARQL beyond as that does not give to find. Well, so we can find. So of course we have a capability within SPARQL to do shortest path. Yeah, where you just specify shortest path between 2 points that you have, and you will get a path object that has multiple elements that you then could filter on if it's in a particular geospatial area. Yeah, so that's how you could combine graph search with geospatial search. But this is not supported in SPARQL. We could do an A-star search, yeah, where you actually, every time when you generate nodes for children, you choose that point that is closer to the destination in the hope that that will give you a shorter path. But that's not in SPARQL, but you can do that in Prolog easily. All right. What is the largest data size you've done this with? The largest we've done is vertically is 22 billion triples, yeah, with several weeks of telephone data in a very compressed form. So that's it. Okay. Well, thank you very much for your time, and we'll send out the video and the recording of this within a day or two. And please send us emails, yeah, if you have any more questions.